This is FRM Part 1, Book 2, Quantitative Analysis, Chapter 13, Modeling Cycles, Moving Averages, AutoRegressive Models, and then we'll combine the two. Let me just quickly remind you what we did back in Chapter 12 and then some previous chapters with multiple regression. Remember our multiple regression example? I'd like to use my boys' performance on their German exams. Back in the multiple regression, what we did is we took some variables, some independent variables like number of hours studied, number of hours playing on PlayStation, number of hours doing whatever it is 14-year-old boys do other than study, and we tried to use those independent variables to determine and explain the variability in their performance on their German exam. What we're trying to do with time series is use a couple of things. In the last chapter 12, we did an auto-regressive model in which we were going to use their past performance on German exams to try to explain the current and future performance, which means that essentially we're going to say something like, if they made an 82% last week, then that's the best way to predict what they're going to do today. That's that AR model. We're going to introduce the moving average model today, in which as this, I'm going to put it in quotes, this independent variable, instead of using past performance, we're going to use an error term from some model that, let's call it white noise from chapter 12. And we're going to use that error term to try to predict the performance on their German test. So notice this is all in this time series analysis where we're using time, a sequence of discrete outputs to measure what's going to happen into the future. So let's look at the learning objectives here. Notice that these all say describe. We have one defined there. So we're going to describe moving averages. We're going to describe the auto-regressive models. We're going to talk about these two guys, Yule and Walker. And then we're going to put them together. Notice that last learning objective says to describe an ARMA process, auto-regressive moving average. We're combining those two and define and describe it. So lots of describes. Let's go ahead and start with the definition of a moving average. And so this is a popular method to model time series. Establishes a linear relationship. All right, so we're going back to simple linear regression and multiple regression, some of those same kinds of concepts, to establish a relationship between an output variable and current and past values of a stochastic term. And remember that stochastic term is not able to be predicted. All right, so in these basic terms, an MA model is a linear regression of the current value of the time series against previous observed white noise error terms. All right, so here's the model. This is called a first-order moving average process. So on the left-hand side of the equal sign, there's our time series, and we have those white noise terms there. So we have the white noise at time period t, which is the current time period, and then the white noise at time period t minus 1. And that t minus 1 white noise variable is going to be influenced by a coefficient. And so note that those terms are defined there. There's the current white noise shock. We're calling that a shock because remember that the expected value of the white noise, the mean of white noise is always 0, and it has a constant variance. And by the way, I remember back in my PhD classroom days, the professor would sometimes describe white noise and say things like, well, it has a mean of 0. And then sometimes he would not say that it has a mean of 0. So I remember thinking, well, maybe sometimes it does, maybe sometimes it doesn't. But in fact, it does. All white noise processes will have a mean of 0. Has a lot to do with the finite power processes and spectral density, if you guys remember that stuff from your old time math days. But anyway, just remember that that has a finite variance, and it has a finite and constant variance and a constant mean, which is going to be 0. And so the number one, that moving average parentheses 1 means that it's a lag of just one step, which of course means that we could probably go back more than one step. We'll do that here in just a minute. But first, let's take a look at an example. And this moving average process has lots of good applications. Of course, as a financial risk manager, you're trying to do things like predict what's going to happen at the next step. Like maybe what's the stock price going to be tomorrow? What's the bond price going to be tomorrow? What's the price of the credit default swap going to be tomorrow? So it has lots of good finance and financial risk management applications, but also has lots of economic applications in terms of trying to figure out, what's going to happen tomorrow. Like in this example, daily demand for fans that is going to depend on the outside temperature. I did read a really fascinating application of the moving average process. Let me just take 10 seconds here to say this to you. I recently had an MRI on my neck because I got this big bulge in my neck and pain going down my left side. But an MRI and a CAT scan is essentially a picture of your spine, taken at, pretty quick intervals. And so it goes up your spine and goes up your spine. And so you can use this moving average to predict what the next picture is going to look like for your spine. I'm sure you guys don't care about the bulge in my neck. Anyway, so here's an example. Daily demand for fans. We have that demand on the left-hand side of the equal sign, and then the two white noise terms on the right-hand side, and they're adjusted by a demand factor of 0.2. So here's some really cool applications and implications and inferences that we can make based on this, what looks like really a simple model. And so if we're using only the current period's error term, then the daily change in temperature is positive. If it is positive, then the daily demands would also be positive. And so that makes sense. I mean, if the temperature today is 90 and then the temperature tomorrow is 95, that must mean that, hey, that makes some sense that demand would be positive as well. And then if we go back to 2 days ago or 1 day ago, if that error term is also positive, then we would expect, and notice I love this, I love the way this is termed, an amplified impact on our daily demand for fans by a factor of 2. And so that makes perfect sense too. I mean, if the temperature is, let's say 88 and then 92 and then 95 and then 105, you amplify that. I mean, you think about, okay, the temperature can't stay hot forever. And then the next day it's 95 and you think, oh, I'll just hang on for one more day. And then it's 98. You're hanging on, and sooner or later you say, oh, I got to do that. So there are people that buy fans when it's 80 degrees and then people that buy fans when it's 95 degrees. And so somehow this model captures that. Here are some properties. The unconditional mean is 0, which should make perfect sense based on our white noise conversations from before. The unconditional variance then has to be a function of that theta, which is, here, let me just go back here really quickly. There's that theta. And by the way, we're going to be tempted to use, just our regular linear regression ordinary least squares to estimate that, but it gets a little bit more complex. I'll tell you about that in just a second. So what was I saying here? That unconditional variance then has to be a function of that theta. And there it's broken down into its parts in the middle blue box. Conditional variance then is just sigma squared, of course. And remember, that's conditional on all of the white noise terms from, epsilon sub t all the way back to t minus 1 and t minus 2. Now, there's this concept of inversion that's pretty important here. Here's the thing. Remember that any stationary moving average process can be expressed as an autoregressive infinite process that we talked about just briefly here a second ago and then in the previous chapter. But if that theta term is less than 1, absolute value of it is less than 1, then the infinite time series process then converges to a finite value. And then we say that it can be inverted. And that's important here. And so we're inverting it, and so that's what we're doing in that blue box there. This is referred to as the autoregressive representation. There's that infinite process that I was talking about just a second ago. So look at that first circle point there. This process of inversion enables the forecaster to express current observables in terms of past observables. So my children have this German test today. So whatever they perform today can be explained by their performance in the past. And there's that last block point. Absolute value has to be less than 1. Now, of course, as I said before, we don't have to just limit ourselves to going back just one period. We can go back way, way as far as we want. And this has greater applications. You know, I remember sitting in that, actually I was laying in that tube for my MRI on my neck, and I was in there for probably 45 seconds. And those of you that have had an MRI, you know that, there's a lot of banging going on. Boom, 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 boom. So I really don't know what's going on there, but it sounds to me like in trying to apply this to a time series that they're taking pictures, every second or every half a second or every 2 seconds, whatever it is. And so, boy, in 45 minutes, how many seconds are there in 45 minutes? I really don't want to do the math very quickly, but you can imagine that you might want to go back to the beginning, that first picture of the first part of my spine, maybe down here to get all the way up here. I don't really know what I'm talking about with science, but it makes some sense. And so notice those are the white noise error terms. And so this MAQ, Q stands for this generalized representation of the MA1. And so you can go back all the way as far as you really want to. So it's important to remember, look at the third block point, that the MAQ and the MA1 process are similar in all aspects. Now, look at the last one here. When Q is greater than 1, that lag operator polynomial will have Q roots. But there is a chance that you could get some of those complex roots. Remember, when do you learn about complex roots and imaginary numbers? I remember thinking these mathematicians, these men and women are so smart to come up with something. What is the square root of a -1? Oh my gosh. All right, so here's some of the properties. We know that it's covariant stationary. We talked about the invertible mean. We talked about the invertible process. The conditional mean depends on the first lag if it's an MA1, and where if it's an MAQ, it's going to depend on all of those other lags. And then here's an important one, this fourth one, the autocorrelation functions. So that if in the MA1 case, all the autocorrelations beyond 1 are going to be 0, and then beyond Q in the MAQ one, those are going to be 0. I do remember back in my graduate days, we used Excel, and we did all this stuff, and sure enough, I remember it was kind of like magic. They all came out to be 0. All right, how about swinging back to the AR model? And so there's the time series on the left, and on the right-hand side of the equal sign are those previous values of that time series, and they're all going to be weighted by some coefficient. Okay. Now, this AR1 is an autoregressive process where the current value, YT, is based on the immediately preceding value plus some error term. And that error term is going to be white noise. And a lot of people think of it as a shock. Remember, if the mean is 0, then the only thing that can happen is of interest. I mean, think about a mean of 0. Let me just draw a line here like this. Think about a mean of 0, and you got a bunch of values that are a little bit above and a little bit below, and they kind of cancel each other out. But suppose you got one way up here or way down here. And so lots of researchers interpret that as a shock, like a shock to stock prices, or a shock to credit default swap prices, or a shock to a credit rating. And that theta is the coefficient of the process at time t-1. All right, so that last block point, let's look at just a GDP growth series. Since we've done this in some previous chapters, the autoregressive model AR1 is going to use only the information on GDP observed in the last quarter to predict that next quarter. Now, once again, we're probably tempted to use some kind of an ordinary least squares model to estimate that coefficient. But it's probably not going to be as easy as that. And I'll talk about that here in just a second. So here are the properties of an AR1 process. The AR1 process is covariant stationary only if theta is less than 1. The AutoRegressive process is always invertible, unlike the MA1 process, which relies on theta being less than 1. There's the unconditional mean of 0. There's the unconditional variance. And there are the conditional mean and variances as well. All right, so here, getting back to this process of, can we use that regular old OLS? And the answer is probably not. So to estimate those autoregressive parameters, such as theta, we're going to need this Yule-Walker process. Now, what Yule-Walker is going to do, it's going to help us determine the entire autocovariance sequence, which means that for any value that we have today, that we're going to be able to predict that value tomorrow. Let me show you what that means here just mathematically. So if we begin with an AR1 model there in the top light blue box, and then we're going to play one of these math tricks. I remember learning this back in, I don't know, maybe 7th grade, where my 7th grade math teacher said, hey, let's multiply both sides of the equal sign by some number, and it doesn't change the equal sign. But what it does is it allows us as 7th grade math students to work down and find some other kind of a result that has maybe some application to something else. So I remember thinking that multiplying both sides of the equal sign by the same thing is really a cool part of mathematics. And so all we're going to do is multiply both sides by the time series at time t minus tau. All right, and so we get that middle, little bit darker blue box. And then if we assume that tau is greater than or equal to 1, and we take the expectations of both sides, we get that gamma tau is equal to, there's our theta, and all we're doing is kind of doing some factoring there. And that's the Yule-Walker equation that we're going to use to estimate theta. And notice that's a little bit different than just using ordinary least squares. All right, so when we're going to do this, we're solving for these autocorrelations. Remember, the autocorrelations are just the correlation between the sequential error terms. And so we're going to use that following relationship where rho at time t is equal to theta raised to the t. And if we do this using some software, we maybe get a result like this where theta is equal to 0.7. And so using this concept derived from the Yule-Walker equation, that first period autocorrelation is going to be the 0.7. The second period is going to be 0.7 squared, and then 0.7, and so on as we go through those final autocorrelations. Now here's the general pth order of the autoregressive process. And so all we're doing is taking my children's performance on their last German test and their performance on their second to last German test and third, and et cetera, et cetera. And so notice that error term at the far right is white noise. This process is going to be covariance stationary, and it's going to behave similarly that we found. Those autocorrelations are going to behave similarly as in the AR1 process. Now, how about if we combine the moving average and the autoregressive models to obtain a better approximation of that Wold representation that we discussed back in the previous chapter. Now, remember what this dude Wold said is that every covariant stationary time series is really the sum of two time series, one that's deterministic and one that is stochastic. So what we can do is we can throw the AR and the MA into a time series model so that we can get the subtleties of each model to be able to better accurately predict and make inferences from that time series. Now, the reason that this is so important is that this is going to be a great model for time series that show signs of seasonality. Now, remember that seasonality is most apparent when those autocorrelations for a data series do not abruptly cut off, but rather decay gradually, and then every time there might be a periodic spike. And I do remember looking at my Excel spreadsheet back when I was in graduate school, and we could see these autocorrelations, and they would just fall by a little bit, or around the same amounts, and then all of a sudden there would be something different in there. And so that's what's happening with this model. So let's take a final example here. There are some observable variables of a time series. Let's suppose that it's Gaussian white noise. And we're just going to use our regular old moving average 1 model and substitute those values in there. And so that time series and time period t is going to be 058 based on all the stuff that we've talked about during this chapter. I think that takes us to the end. Next up is volatility.